Okay, let's begin. I gotta start by saying my voice is a little shot, so apologize for that. So you may want to come down because I can't really shout, and the air pollution doesn't help. So. Okay, try to get to where we are from last week. How many of you attended the review session on Friday? Okay, not too many. Okay, but I hope you're all trying the problems at home. I assume that means you've done it at home. And you don't need to, because it's important that you're able to do those problem sets yourself. Because remember, the quiz and all that will be very much related to what you're doing there. Okay, so last week we basically learned how electrons populate energy levels in different kinds of materials. I'm just trying to get to the last slide, which is what we forgot. Okay, which is there. Okay, so if you recall, we talked about atoms, discrete levels, and we talked about when atoms come together, they form crystals where you have energy bands. Now, the last part of this chapter talks about a very specific kind of material, which are called quantum wells. I just wanted to introduce this concept here, and we'll come back to this when we talk about semiconductor lasers later in the class. But quantum wells are a very specific kind of a crystal where you can engineer the band gap. So obviously you can see the advantage of this because you can, if you can control the band gap, you can control the frequency of light or the wavelength of light that could be emitted from such a semiconductor. So a very typical example is shown here. This is aluminum gallium arsenide sandwich between two aluminum gallium arsenide layers. So these are grown epitaxially like we saw in the first lecture. So you grow aluminum gallium arsenide atom by atom on some substrate like germanium or gallium arsenide or something. And then you stop, and then you grow pure gallium arsenide for about 50 angstroms, 5 nanometers. So very thin. Okay, and then you continue growing aluminum gallium arsenide again. If you do something like this, so this is the growth direction. Okay, so this is the cross section through the wafer, what you're looking at. You can if you look at the band diagram of such a device, you see there is a high band gap for the aluminum gallium arsenide, 1.35 eV. And then suddenly the band changes to 1.43 eV, and then it goes back up to 85. Okay, so you can have two different crystals, have different band gaps. If this is done perfectly, then there is no lattice mismatch, so it looks like the same material, no defects or anything. Okay, they match each other. The same lattice constant, same crystal structure, everything else is the same. But of course, the electron will see this band difference. Okay, now for an electron which is trapped in the conduction band, it looks like it's a particle in a well. Okay, you have a high potential here and a low potential here. So the electron is kind of trapped in this well. Of course, this well is not infinite; it's finite. So the energy levels will be different. But nevertheless, it behaves more or less like a particle in a well. So you have discrete energy levels. Same thing happens for the holes. Of course, for the holes, remember the energy is increasing downwards. Remember from last class. So you have, again, a particle in a well analogy. Now, the point of this is that you can control where these energy levels are by controlling two things. One is, what is this band gap? Because you can change that band gap by changing the aluminum concentration. Remember, we talked about this last class. And the second thing you can change is the thickness of this layer. By making it thinner or thicker, you can also change the energy levels. What that means is that you can change these energy levels, this EH, E1, and so on, arbitrarily. So essentially, you're creating an artificial atom, if you think about it. You're creating discrete energy levels that can be engineered. So it's quite powerful, if you think about it. Okay? There are other ways to do this as well. We'll talk about that later on. But you can imagine if an electron and a hole here recombine and emit a photon, its energy will be controlled by that energy band gap difference, energy level difference, right? So if you can control that, you can control the color of the light that comes out. So for instance, this is how you can make different colored LEDs or semiconductor lasers. Okay. We will revisit this, but it's just for completeness. For now, you should be aware of it. So this is a method to engineer the artificial discrete energy level. So it's like an artificial atom. It's useful for light-emitting devices, light-emitting diodes, semiconductor lasers, and so on. Okay. So to summarize this chapter here, we looked at charge carriers in semiconductors in three systems. Atoms, we had discrete energy levels. Again, keep this in mind. And when the atoms are brought together, the energy levels smear into bands. The band gaps, in the case of insulators and semiconductors, and no band gaps in the case of metals. And that determines conductivity, whether it's a good conductor of electricity, good conductor of heat. Okay? And finally, we talked about the quantum wells, which creates discrete controllable energy levels. Okay? So that is the end of that topic. And today we are going to get it up the next. We are going to talk about how to calculate the concentrations of the carriers in the semiconductors. So far it has been qualitative, like where the electrons are, what happens, what are electrons, what are holes, so on and so forth. But today we are going to understand how to calculate how many electrons are there, how many holes are there. And on Thursday, we will use these concentrations to calculate what the currents are. So that's the logical progression, if you want to keep the big picture in mind. Okay? So, the math is fairly straightforward, but we have to make some assumptions.
No.
Oops. I don't know what that was. Okay, so carrier concentrations in semiconductors. Okay. So, like I said, we need to understand how many electrons end up in those energy levels. So we know there are energy levels in the valence band, there are energy levels in the conduction band. How are the electrons distributed there? Because we need to know how many electrons are in the conduction band to calculate the current, remember, and how many holes are in the valence band to calculate the current. So this is the goal that we're trying to achieve today. Okay? In order to do this, we need to understand what's called the Fermi level, and we'll go to that in a second. And this turns out to be an extremely important concept in semiconductor physics, device physics, and we'll come back to this again and again. So make sure you really understand this idea of the Fermi level. Okay? The first thing we can say, the easiest thing we can say is that the concentration of, so remember, in an extrinsic material, we add donors or acceptors. If you have a donor atom, it donates one electron, remember? Okay? So one donor atom is equal to one electron, which means that in an N-type material, if there are N, or capital N, donor atoms, there are capital N electrons. Okay? That means the concentration of the electrons is equal to the concentration of the donor atoms. Okay? That's a straightforward common sense thing to assume. Okay? As long as one donor atom gives one electron. And the same thing for holes. The concentration of holes in the valence band is equal to the concentration of the acceptor atoms. To generalize this, we can say the concentration of majority carriers, which are electrons in the N-type, or holes in the P-type, are equal to the corresponding donor or acceptor atoms, respectively. Okay, so that's fairly straightforward, common sense. Okay, that's the first thing we can say. However, the concentration of the minority carriers is much more complicated. Now, it turns out the minority carriers are quite important to do current calculation. So we need to understand that. Okay, and also how the carriers populate the available energy states as a function of temperature. It's also quite counterintuitive. We need to understand that as well. Because you have a temperature dependence of, if you have a device that needs to work within a fixed certain temperature range, you need to be able to predict what the currents are within that temperature range. So you need to understand the temperature dependence as well. So these are the two important things that we're going to try to quantitatively understand today. Okay. The first concept comes from what's called the FermiDirac Statistics. Now, we won't derive this, but for those of you who are interested, it's in one of the appendices of the book. I think it's Appendix 4 or something like that. You can go through it. It's not that difficult. But basically, the assumption is that every electron is indistinguishable from every other electron, which is straightforward. These are what are called fermions. So you might have heard from your undergraduate physics classes there are different kinds of particles, fermions and bosons. Fermions are particles which are indistinguishable from each other, where bosons are distinguishable from each other, and they have very different spin properties. Okay? Electrons tend to be fermions. Okay? And what that essentially means is that if you apply the principles of quantum mechanics and apply Pauli's exclusion principle, remember that two electrons cannot occupy the same four quantum numbers, you can prove that the electrons obey what's called the FermiDirac statistics. Okay? It sounds complicated, but it's actually very simple. All it is if you have an energy level, E, let's say, anywhere, it doesn't matter, it can be a band, electron, atom, or a quantum well, whatever, what is the probability that that energy level is occupied by an electron at a certain temperature? Or in the case of a hole, it's the opposite. The energy level is occupied by a hole. Okay? But let's focus on electrons for now. Okay? The FermiDirac statistics is essentially a distribution that gives the probability that an energy level, E, is occupied by an electron. Pretty straightforward. And it's given by the equation. That's the so-called FermiDirac function. Okay? So f of E, where E is the energy level in consideration, is 1 over 1 plus an exponential function. Okay? Where the exponent is E minus EF. E is the energy we're interested in. EF is the so-called Fermi level, which perhaps is the most important concept in semiconductor devices. And we'll keep coming back to this. Divided by KT. Okay? Of course, EF is the Fermi level. K is the so-called Boltzmann's constant, which you've seen before. It's about 8.62 10 raised to minus 5 electron volts per Kelvin. And T is the absolute temperature. So a couple of things you can think about right now, just by looking at this. As E minus EF increases, it's an exponent, and if it's a positive number, this whole thing increases fast. Right? It's an exponential growth. This means, since it's in the denominator, this probability goes down very fast. So if the E, the energy level we're interested in, is far away from the Fermi level, the probability that that energy level is occupied is very low. Makes common sense, as we will see. Okay? And of course, the other dependence is temperature. As temperature increases, what would common sense dictate? As temperature increases, the probability of an energy level being occupied. It should increase, right? Because remember, the electrons can gain energy and go up to whatever energy level. So whatever energy level it is, the higher the temperature, the probability has to increase. And clearly it makes sense. If T increases there, this 1 over T decreases, the exponent decreases, and the whole thing increases. Okay? Because it's in the denominator. Pretty straightforward. Okay, so let's do a very quick example. What is the probability, and I want you to discuss with your neighbors, that the Fermi level is occupied by an electron? Okay? Okay, I'll go back to the equation. Now discuss. Set E equals EF, basically. Take 10 seconds. It's very easy. Okay, we can stop. This doesn't require too much discussion because all you need to do is that E equals EF. And that becomes 0. What's E raised to 0? 1. So what's the probability? Half. Right. So the definition of Fermi level is essentially, it is the energy level in any system where the probability that that energy level is occupied is 50%. Okay? It's a nice metric if you think about it conceptually. Any energy which is higher than the Fermi level has a lower than 50% probability of being occupied. Because as E minus EF increases, the whole probability decreases. Okay, well, we'll look at the graph, but I want you to understand this conceptually first. On the other hand, if E minus EF is negative, what happens? Let's say the E is less than EF, which is also possible. What happens? The exponent becomes negative, which means you can bring it up to the numerator. The whole thing increases. Which means as the energy level goes below the Fermi level, the probability of it being occupied goes above 50%. Okay, so do you see the conceptual significance of Fermi level? It gives you roughly the 50% probability level. Anything above that, lower probability. Anything below that, higher probability. Okay, so keep that picture in mind as we will look at the graph. Again, it's much more important that you understand these things conceptually rather than the math. The math's pretty straightforward. So this is what we just talked about. Okay, that's what the FermiDirac distribution looks like. Okay, so the vertical axis is f of E, the probability that the energy level is occupied by an electron. The horizontal axis is E, the energy. Okay, so of course, let's look at the easiest thing is let's look at the Fermi level first. We know that the probability should be half. Okay, so that's half. Pretty straightforward. If the energy is below EF, of course we know that the probability must be higher than 50%, just from our discussion just now. If the energy is above, it should be less than 50%. Clearly it is. Okay, and of course there's a temperature dependence. So let's talk about that first. The first, let's look at the blue curve. Okay, at T equals 0 Kelvin, absolute 0. Okay, if you look at the equation, 1 over KT, at T equals 0, so let's start this back here. It's very important for you guys to understand this qualitatively. That's why I'm trying to spend some time on understanding it. Rather than the math, it's less important than that. If T goes to 0, what happens? This is 1 over T goes to infinity. No? E raised to infinity is what? It's infinite again. And 1 over infinity is 0. Yeah. The whole thing goes to 0 as long as E is greater than EF. Okay? So it becomes a step function. You have a question?
I just have a question. So the Fermi level is where the electron should be ideally?
We'll come to that. It's a very important question, actually.
So that's where it would be ideally, and they just kind of spread out.
But hold that thought.
Okay.
We are going to come to it. Yes. It's a very good question, actually. Very important question. So let's just think about the simplest situation first. T equals 0. Nothing is moving. Okay? So we know very easily that any energy above the Fermi level, probability is 0. Okay? Very straightforward. Of course, if you think about it, it makes sense. No electrons have energy to go anywhere, right? It's just sitting where it is. But if E is less than EF, what happens? This becomes negative. This goes to negative infinity. E raised to negative infinity is infinity. Sorry, it's, you have to bring that up, remember? I got to write this properly. So this becomes something like that. This is 0. It becomes 1. Okay? In other words, the probability is 100% that the energy level below EF is occupied at T equals 0. So it's essentially a step function as shown by this blue curve. Okay, it's 1 until the EF and goes to 0. Okay, and all these will make sense in a few minutes when we look at how, in the context of the semiconductors. Okay, but just think from the distribution first. As the temperature increases above 0 Kelvin, what happens is that you have a finite probability, as you see here, that energy levels above the Fermi level are occupied. So this probability was 0, but now it's no longer 0. You have some number. Okay? It should make sense because some of the electrons have gained energy to get into some of these energy levels. And we'll put this in context of valence and conduction bands shortly. Okay? Another important property to think about here, also the same thing happens over here. At T greater than 0 Kelvin, there is a finite probability that the energy levels below the Fermi level may be unoccupied. Okay? So remember, F of E is the probability that an electron exists at that energy level. So 1 minus F of E is the probability that the electron does not exist. It can either exist or not exist. Only two choices. Yeah? This is equivalent to saying there is a hole at that energy level. Right? Because there's no electron. Absence of an electron is a hole. So what this is saying is that at greater than 0 Kelvin, there is a finite probability that you can have holes at that energy level. Okay? Now if you think about it, what has happened essentially is that the distribution is symmetric about the Fermi level. In other words, this happens because an electron has gone from here to here. If you think about it. So the probability that a state here is occupied is equal to 1 minus the probability that a state over here, a symmetric state over here, is unoccupied. Okay? So remember, electron came from one side and went to the other side. So they have to be equal. It has to be symmetric, considering everything else. Mathematically, of course, we can write it this way. Okay? But again, I don't really care about the equations. I want you to understand this conceptually. Okay? F of EF plus delta E, so some energy here, should be equal to 1 minus F of EF minus delta E. In other words, this distribution is always symmetric about the Fermi level. And of course, the probability at the Fermi level is independent of temperature. It's always half. Right? So this thing goes to 0. It doesn't matter what the temperature is. Okay? So keep these things in mind. Okay? Now we're going to put this in context of the semiconductor and try to address that question that he asked. Okay? So, remember, the first thing to recall here is that F of E is the probability that an energy level at E is occupied. Okay? That doesn't say the full story. In other words, you need to have some energy levels available first at E. Recall that if you have a band gap in a semiconductor, within the band gap there are no energy levels. So even though you might have a finite probability that within the band gap that electrons could exist, but there are no available energy levels, they cannot exist. Okay? So F of E is not the full story. You have to understand how many energy levels are available as well. Okay? And this is defined by what's called the density of states, or density of available energy levels. Okay? And this is what we draw when we draw band diagrams, pretty much. Okay? Let's look at this first, visualize this. To visualize this, what we need to do is we need to flip the Fermi level 90 degrees. Okay? So now the horizontal axis is the probability, F of E, and the vertical axis is energy. Okay? And we overlay the FermiDirac distribution with our well-known valence band conduction band diagram. Okay, simple energy band diagram. So that's what's shown here. So you have a valence band, you have a conduction band, and you have the Fermi level here, and this is the distribution. Okay, pretty straightforward so far. Nothing strange. Remember, this is okay because, of course, this diagram represents electron energy going up. So this is okay, what we've drawn. Okay, it's nothing strange here. We just put the two diagrams together. Now, If we have an intrinsic semiconductor shown here, we know that there are, first of all, we know that there are no energy levels in the band gap if you have an intrinsic semiconductor, no donor levels, no acceptor levels, which means that, of course, there are no energy levels means that no electrons can exist in the band gap with that energy because there's no available levels. Okay? Although that the probability of an energy level, energy being occupied here is non-zero. There are no energy levels available, so there are no electrons. So you have to multiply these two things together in order to understand how many electrons there are. Okay? Now, let's look at that a bit more carefully. In an intrinsic semiconductor, the concentration of holes in the valence band is equal to the concentration of electrons in the conduction band because electron came from here and up there. Okay? Which means that the Fermi level lies very close to the middle of the band. Okay? Why? Because, of course, if you think about it, from a very simplistic perspective, we know that the FermiDirac distribution has to be symmetric about the Fermi level. If at this energy level there are the same number of holes as this energy level, that means this Fermi level has to be halfway in between, because otherwise it will not be symmetric. Do you see that? Just qualitatively. In actual practice, it's a little bit different because it has to do with the effective mass. The effective mass of the electron in the conduction band is a little bit different than the effective mass of the hole in the valence band. But we'll ignore that for now. We saw effective masses last class, so you should appreciate that. But let's put that aside. But with that caveat, we can say in an intrinsic material, the Fermi level will be very close to the middle of the band. We know that the probability that the energy level there will be occupied by an electron is half, 50%. But of course, there is no energy level there. Right? It's a band, energy band gap. So there are no electrons there. As simple as that. Okay? Now, here, so that's what it's saying. Although f of e is greater than 0 here, there are no available levels, so no carriers there. Okay? We'll quantify this in a second, but I want you again to understand this qualitatively. Now, of course, there are available energy states up here and down here. Up here, there are conduction band states. Down here, there are valence band states. So, if you look at this little inset here, which is magnified up here, the number of carriers here can be calculated very easily. You look at the number of available states, which is, we can calculate, we'll talk about that in a second, which is determined by the valence band, multiplied by the probability that those states are occupied, which is just given by f of EC at the conduction band. Okay? So that's why this sort of a diagram is a nice way to look at how many electrons are in the conduction band or in the valence, how many holes are in the valence band, and so on and so forth. Okay? Again, we'll look at more cases, so it'll drive home this point. One important thing to remember is that the number of available states here are huge compared to the number of intrinsic carriers at room temperature. Okay, yeah. We will see this also in a second, but their orders of magnitude different. So the number of intrinsic carriers is about 10 raised to 10 per centimeter cube, if you recall, at room temperature for silicon. But the number of available levels at 10 raised to 19. You have 9 orders of magnitude more levels available. What that means is that any small changes in probability here can make a huge change in the carrier concentrations because you have so many levels available. Orders of magnitude. So that's why this FermiDirac distribution is extremely important for all devices. In fact, when we talk about transistors and so on, we'll draw the Fermi level. We'll try to qualitatively understand what's going on. So you need to understand this conceptually now. Okay? So any small changes in the f of E by temperature or whatnot can make huge changes in the carrier concentration. Okay. Of course, we can do the same thing for N-type and P-type material. So let's take a quick look. The N-type material, the Fermi level, first of all, in an N-type material, ignore the Fermi distribution for a minute. Let's just recall. In an N-type material, there are many more electrons than there are holes. Okay? So you have a few holes in the valence band, many more electrons in the conduction band. Okay. If you conceptually think about it, what does that mean? That means that the Fermi level has to be closer to the conduction band, right? Because the energy level, there are many, many more electrons here. And remember, the distribution always has to be symmetric with respect to the Fermi level. Okay? So it is true, the Fermi level is closer to the conduction band in N-type materials since there are a lot more electrons than holes. And it looks like that. So EF is somewhere there. And, and you can never also generalize as the Fermi level moves closer to the conduction band by a variety of ways, by increasing impurities or increasing temperature or whatever, and we'll talk about this again. The electron concentration in the conduction band increases compared to the whole concentration in the valence band. Okay. Of course, you can also conceptually see this, right? If you zoom in here, the probability that there are electrons here is this probability. The probability there are electrons in the valence band is equal to the probability distribution from the FermiDirac distribution, which is the probability that any energy level is occupied, multiplied by the number of available levels. Okay. So when the Fermi level moves closer to the conduction band, this f of c increases, right? Because the distribution is shifting up. We can visualize that. Okay. And the same thing happens, the whole concentration of the valence band decreases symmetrically, right? If you look here, as this curve moves up, this number will get closer and closer to 1 exponentially. Of course, what does that mean? That means all the levels are occupied, there are no holes, no free levels. Okay. The opposite, of course, happens for the p-type. In the p-type material, the Fermi level is closer to the valence band because there are many more holes than electrons. And the same thing, as the Fermi level moves closer to the valence band, the concentration of holes in the valence band increases and the concentration of electrons in the conduction band decreases. Okay. Now, for now, I want you to again go back home and think about this conceptually. We'll look at the math. Math is relatively straightforward. Conceptual understanding is much more difficult. So I want you to always keep that in mind. Okay. So again, for simplicity, we usually only show the Fermi level. We never show this distribution. So for simplicity, you can assume just showing that part, just the bands and the Fermi level. Why? Because the Fermi level gives you the 50% probability point. And if you know the temperature, you know the distribution. You don't need to actually draw it. So it's a simplified version of it. Okay?
No, or that the FermiDirac distribution function is a soup kitchen? That's preposterous. Your Honor, the FermiDirac function is, for any system of identical fermions in equilibrium, the probability that a quantum state of energy E is occupied. My word, man, don't you know your quantum statistics?
So, just a diversion, but recall what it said. It is true for any fermions, and this is a very fundamental rule, that if you have particles which cannot occupy the same 4 quantum numbers, they need to obey what's called the FermiDirac statistics, and you need to have this sort of a distribution function of how the energy levels are occupied. Okay? I know these things are abstract, but we need to kind of really get this into your head. Otherwise, going forward, we will be lost. So I really recommend going back and really thinking about this, okay? Because we are going to go into much more deeper things. And this is, I would say, the start. So now, with this very qualitative understanding, let's try to quantify this. Let's try to calculate how many electrons there are actually. Okay? So far, we have just looked at the pictures, right? All right. The calculation is very straightforward. We just talked about it. The electron concentration, N naught, where the 0 is just a matter of saying it's at equilibrium. Okay, equilibrium means, remember, generation and recombination are matched. So the number doesn't change with time. It's a fixed number. Okay? It's given by an integral. It's an integral of electrons in the conduction band in this case. The integral goes from the bottom of the conduction band to infinity, all the way, okay, of a product of f of E, which is the probability that an energy level E is occupied, multiplied by n of E, which is the so-called density of states which is the number of available energy levels, times dE. Okay. So again, f of E is just the probability that the electron occupies a Fermi level, which is just a Fermi function. N of E, D of E is the new concept we're introducing here. It is the density of available energy levels between E and E plus dE. Okay? Now, it's a density, which means its units per centimeter cube. What this means is that if you plot E as a function of N of E, let's say you have some function. We'll show it kind of looks like that. It's not important right now. What that definition of N of E means that if you take an energy level E1 here, okay, and you increase it by E1 plus EE. So within the small energy range, the number of available states is given by that. That's what it's saying. Okay. So if you take any energy band diagram, you take a small slice of energy, and you look at how many states are available there, that's given by N of E times dE. This is also the second important concept that we're introducing today, after the Fermi level. Again, it's a little bit abstract. Keep in mind, this is again the number of states that are available. So remember, we draw all the filled states in the valence band, all the empty states in the conduction band. This is the number of states available. Okay, multiplied by the probability. That gives you the number of electrons. Again, try to understand where this comes from. Don't just memorize the equation. That's what I'm trying to say. Okay? Okay. It's common sense if you think about it. Okay, now let's look at how these functions look like in some example band diagrams. Okay? Let's start with a simple intrinsic semiconductor. So let's start on the left. Our familiar valence band, conduction band, Fermi level in the center. Okay? Intrinsic semiconductor, very straightforward. Valence band is filled with electrons. Conduction band is empty of electrons. Or maybe there are a few electrons at room temperature. Okay? And a few holes at room temperature. The density of states function, N of E, can be shown to look like a parabola. Again, we are not going to prove it, but if you're interested, it's in the appendix of the book. Okay? It's just mathematically a bit involved. But in any case, if you look at the density of states, so in this case, it's plotting N of, so it's flipped around from what I drew here. This is energy going up. This is the density of states going up. Okay? So what it's saying is that here is that the density of states here is that number, whatever that is. Okay? Then it increases in a parabolic fashion as you go up. So higher energy has higher density of states, more available energy levels. That is actually an important idea, turns out. We'll come back to that. And down here, of course, we do the opposite because it's the holes. The energy goes down. Energy for the holes increases downwards. Okay, so same thing, but it's relatively symmetric. Yes?
What's the horizontal axis?
Horizontal axis right now, remember, this is the band diagram. So we don't, in theory, it's the K vector. If you think about going back to the band diagram with three-dimensional, but we are going to ignore that. And we're just going to, there is no variable in the horizontal axis right now. Well, in this diagram, in here, this is the N of E. This is this number.
Okay.
Okay, and the different curves are different. I'll show you in a second. Okay, and here's the Fermi f of E, right? FermiDirac Fermi probability. Okay, so just the function here. Then, if you multiply these two together, so these are the available states. This is the probability that the states are occupied. If you multiply them together and do the integration, you get the concentration. So this is the concentration of electrons, concentration of holes, in an intrinsic semiconductor at room temperature. Okay. Of course, we know this from previous discussion. In an intrinsic semiconductor, most of the electrons will be concentrated at the bottom of the conduction band. Which is exactly what the equations tell us. And most of the holes will be concentrated at the top of the valence band. Qualitatively, you can see this, right? Although let's look at the electrons for a second. Although the available states increase here, So one would expect there are many more states available. Why wouldn't electrons be there? But you can see the probability is very small. It falls exponentially, right? And the product, of course, gives you some optimum value near the conduction band. Same thing happens for holes. Of course, the available states for holes is huge as you go lower or increase the hole energy. But the probability that they are unoccupied is 0, pretty much. Okay? So they're really not there. So both these things matter, the available states and the probability of those states are occupied. Okay? And as a result, we get a distribution which looks like this. This is our goal, concentration of charge carriers. We want to calculate this quantitatively. Okay? So the assumptions are, okay, so this is what I said. Using quantum mechanics and Pauli's exclusion principle, we can prove that the density of state is proportional to square root of E, so it's roughly a parabolic distribution. Okay? The Fermi function decreases exponentially with E, so they are counterintuitive. The one increases, one decreases, right? So they have an optimum in between, and you multiply them together. So the product decreases rapidly because exponent, of course, is much faster than square root of E, right? So rapidly for energy levels above the conduction band, f of E, n of E this is the integrated version, so that's important. In other words, this is what basically saying is what we saw before. Most electrons occupy the bottom of the conduction band, and most holes occupy the top of the valence band. Okay? Again, something we knew before, nothing surprising. Now, let's look at some approximations to get some intuition out of this math again. Okay? Going back to the equation, the electron concentration at steady state is given by the integral. We can write this integral as a simple product of an NC, some constant NC, multiplied by f of EC, where f is the FermiDirac function at the bottom of the conduction band, EC. So this is the probability that the bottom of the conduction band is occupied, and this is just some constant, which turns out to be an effective density of states, or effective density of energy levels at the bottom of the conduction band. Okay? So this is just a way to simplify this integral into something much simpler, okay, by defining what's called an effective density of states at the conduction band. Okay? Now, if you further make the assumption that the Fermi level is far enough away from the conduction band, okay? In other words, if you look at the band diagram, you have the conduction band, the valence band. If the Fermi level, in this case of the Ntype, let's say, if the Fermi level is far enough away from the conduction band, far enough in the sense of much greater than kT in terms of energy, then we can approximate that exponential by just making this assumption. You can recall 1 plus e raised to minus x. If x is very small, and this is, of course, this is a Taylor series expansion. Right? This is approximately equal to, and so on and so forth, right? This is a Taylor series expansion. And we can just write 1 by 1 plus e raised to ec minus ef over kt is approximately that. Okay? Actually, this is simpler than, sorry, this is not the Taylor series. I'm jumping the gun a little bit. This is much simpler than that. This is just saying that if ec minus ef is large, that exponent is much larger than 1. So I can ignore the 1. Then 1 over that is just that. Right? Pretty simple. Now, why are we doing this? We're doing this so we can calculate that effective density of states quantitatively, so we can understand what that is. Okay? So this approximation is true as long as the Fermi level is a few kTs below EC. KT is, of course, the Boltzmann constant time temperature. At room temperature, this is a very small number. It's about 26 millivolts or so. So it's pretty tiny. And it's a good approximation in general at room temperature. Then we can write n naught as nc e raised to minus ec minus ef over kt by just substituting there. Okay, pretty straightforward. So you take this approximation, plug it in there, you get that. This is a very important expression. And let's try to look at this qualitatively. Okay. The first thing you will notice, of course, is that as T increases, N naught increases, as expected. More importantly, you will notice as this distance, EC minus EF, which is just this, as this decreases, N naught increases, which is what we said before. As the Fermi level goes closer to the conduction band, the number of electrons increases. Okay? So these things make intuitive sense. As EF gets closer to EC, then naught increases. Effective density states can be shown to depend as something like that. Again, this comes from the appendix. I'm not going to prove it. But you can write the effective density states of the conduction band in terms of KT, the constants, and the effective mass of the electron at the conduction band. Okay? Now recall that the effective mass of the electron depends on the curvature of the band. Okay? So it depends on the crystal structure, which means that the density of states, of course, depends on the crystal structure, which is why we need to know the crystal structure. So I'm tying it back to your first lecture. Silicon will have a different N of E or NC than gallium arsenide. We need to know how the crystal structure is in order to calculate this. In order to calculate the available energy levels. Okay? Not the FermiDirac distribution, because that's general. It doesn't matter what material. Okay, now we can plug everything in. Oh, so it's a good question. What happens is the temperature increases. So why don't you discuss for 10 seconds, 15 seconds? So what happens, let me explicitly state the question. What happens to the electron concentration in the valence band, in the conduction band, as temperature increases? From this expression, so you have NC has some temperature dependence, and you have an exponential temperature dependence. Okay, discuss. Okay, what happens to NC, the effective density of states? That increase or decrease? Okay, right, increases. What happens to the other term, F of E? Increase or decrease? This term, right? Those are only two terms there, so it's pretty straightforward. What happens to that? T increases. We talked about it, so what happens? Huh? TT increase, temperature. Temperature.
The e to the negative is smaller.
Yes, very good. Yeah. So the probability should increase. Okay. So remember EC minus, okay, so we have to think about two things. EC minus EF is positive, right? So the negative sign means that's negative. So as T increases, this term, e raised to minus this thing, decreases. So this whole thing increases. Okay, but make sure you can follow that kind of line. That's just simple, right? So you have two competing things happening. Okay, but of course, which is more powerful, the exponent or the polynomial growth? I mean, the superlinear growth. So exponent, right? Exponent will always dominate. So it is this term that's more important, clearly. Okay. So of course, we'll draw this out in a few seconds, but keep that in mind. As temperature increases, so going back to the answer to this, as temperature increases, of course, the electron concentration will increase, which is what we've been talking so far, but we can also see this just from the math. Okay, just make sure you're all on the same page on that. Okay, now let's do the same thing for the N-type and the P-type semiconductor, again, just to understand this a bit better. Now the band diagrams are very straightforward. Remember, in the N-type, you have the Fermi level closer to the conduction band. It's the only difference, but otherwise the same. The density of states are the same. Doesn't really change very much. as long as the concentrations of the donors in this case are not huge. Okay. Of course, the FermiDirac distribution just moves up a little bit. Otherwise, it's the same. The shape doesn't change. You multiply them together, do an integration. Of course, because this has moved up, the probability here has increased. Right? So, of course, you get many more electrons here. Okay? And fewer holes. Okay? Because the probability here has decreased in terms of hole. Okay. Same thing happens for the p-type, the analogous thing. The Fermi level goes down. Okay. The density of states look the same. Again, it's slightly different, but not very much. The Fermi level, the FermiDirac distribution goes down. So the probability that your holes goes up now, quite dramatically. There's a probability that your electrons goes down. So of course you have many more holes here, fewer electrons there. That's a qualitative picture that you want to keep in mind. Okay? Because we're going to keep coming back to this, as you will see when we talk about devices, PN junctions and so on. Okay. Now, one important note about this effective density of states is how to calculate the effective mass. The effective mass turns out to be a tricky thing, and it depends on what you're trying to calculate. You can have different kinds of effective mass. Remember, last class we talked about what the effective mass is. Effective mass is just a mathematical construct that helps you to do the solution of Schrodinger's equation simply. It's a simpler version. Okay? It's not real. It's just a mathematical number. But it depends on what you're trying to calculate. So there are different kinds of effective mass. Here we're talking about what's called the density of states effective mass. Okay? That's, of course, because we are calculating the density of states, the conduction band in this case. Okay? So the effective mass in this situation needs to be calculated at the bottom of the conduction band. In silicon, from the silicon diamond lattice structure, we know that the 6 equivalent x directions, which is the bottom of the conduction band. Remember, x is the bottom of the conduction band. There are 6 equivalent directions where that happens. So you have to average them, basically. You have to average them in a specific manner. So if you recall, we had the equal energy diagram that we saw maybe last lecture or the lecture before. But in momentum space, we drew the equal energy diagram, and we saw it looks like an ellipsoid. So you have of course the curvature of this is the mass, basically. Remember, the curvature of the band determines the mass. This is the equal energy diagram, which is pretty much the band. Okay. So you have a transverse mass in the x and y, and then you have longitudinal mass in the z momentum directions. And the effective mass for the density of states turns out to be what's called the geometric mean of these effective masses. Okay, so it's 6 times square root of ml, ml mt squared, and then raised to 2 over 3. So it's what's called a geometric mean. And we are not going to prove this, but you can derive this from dimensional constraints. Okay? Again, you don't need to memorize this. You can look this up if needed. But just keep in mind that the density of states depends on the effective mass, and the effective mass depends on the curvature or the shape of the band, which of course depends on the crystal lattice. Okay? For gallium arsenide, this diagram is a sphere. Okay, remember it's a direct band gap semiconductor. It's just a sphere. This equal energy diagram, which means that the geometric mean is nothing but the regular mass, effective mass of the electron. Because ml and mt and all that will be the same. Okay. Okay. So for gallium arsenide, the equi-energy surface is spherical, so the density of states effective mass is just you just set ml and mt equal to each other, essentially. Okay. Less important right now. Okay. Now, so far we have only calculated the electron concentration. So how do we do the hole concentration? Again, it's straightforward. We have an analogous expression. Essentially, we have an effective density of states, effective density of available energy levels at the top of the valence band, which is NV, okay, multiplied by the probability that the top of the valence band is unoccupied, right, because it's a hole. So it's 1 minus the Fermi distribution at EV. Okay? So it's probability of finding an empty state at EV. And again, we make the same assumption that the Fermi level is far enough away from the valence band that we can make this approximation and write the 1 minus 1 over 1 plus e raised to EV minus EF over KT as e raised to minus EF minus EV over KT. Anyway, just a simple approximation, just like before. Okay, you can do this yourself. It's not that difficult. Now, EF is greater than EV by a few KT's assumption here. Again, KT is about 26 millivolts, so it's pretty small. So it's a reasonably accurate assumption at most, at room temperature. So, okay. Then you get an expression which looks like this. P naught is NV, which is the effective density of states at the top of the valence band multiplied by the probability, okay, which depends on the distance of the Fermi level from the valence band. So in this situation, of course, we have EC, and the Fermi level is closer to the valence band, and this energy difference is what matters for calculating the whole concentration. Okay. And NV again is given by a representative equation as shown there. That's again something that depends upon the effective mass of the hole in this case. So you can see that the NC and NV are they have the same equation, except that the effective mass is one is for electrons, one is for holes, and they can be different, right? Because the curvature, band curvature is different. For gallium arsenide, it's roughly the same, but silicon they're different, which means that you can have different concentrations of available states for holes than you have for electrons. Which means that you have to treat them carefully. You cannot just assume whatever electron does, the hole does. So when you do current calculations, you actually have to do them one by one, separately. We'll see this next class. Okay? Okay. So so far we haven't made any assumptions as to whether the material is extrinsic or intrinsic, whether it is doped or not. So these equations can be applied no matter whether it's intrinsic or extrinsic. So we can write, in the case of an intrinsic material, we can write Ni instead of No, okay, to represent the intrinsic, and the Ei to represent the Fermi level of the intrinsic material, which we know from before should be close to the middle of the band. Okay, and the same thing for holes. Now, the product of the carrier concentrations is constant at a given temperature. Okay? This is true even for extrinsic semiconductors. Okay? Because as temperature increases, the number of carriers can increase, but it's only at the cost of the other one. Okay? We will see this again. Okay? So we can multiply these two things together. In an intrinsic semiconductor, this is clearly obvious, right? And remember, we saw this last class. In an intrinsic semiconductor, N naught times P naught equals Ni squared. Ni squared, Ni is of course fixed. It's a constant. Depends on temperature. It's fixed. Okay, so this product depends on temperature, but it should be always equal to Ni squared. So that's what we're trying to do here. So you multiply those two terms together, you get NCNV, e raised to minus EC minus EV over KT, or NCNV, e raised to minus EG over KT, which is nothing but the energy band gap. Okay? So the product of the carrier concentrations in an intrinsic material is exponentially dependent on the band gap, which is shown here. Which also makes intuitive sense if you think about it. higher the band gap, the lower the concentrations, because it takes more energy for the electron to go from the valence band to the conduction band. Lower the band gap, the higher that concentration, because it's higher probability that the electrons can go from the valence band to the conduction band. Okay? This is the reason, of course, why an insulator has very few electrons in the conduction band, whereas a semiconductor has many more electrons in the conduction band. Okay? We're just quantifying it. Of course, you can write this as Ntype, the same thing, because it is true whether it's extrinsic or intrinsic. Doesn't matter. So the equation, the top equation is for extrinsic material, the bottom equation is for intrinsic material. Okay. Okay. Now, let's concentrate on the special case of the intrinsic material. In the intrinsic material, remember the constraint is that there are no donors or acceptors. One electron from the valence band goes to the conduction band, creates one hole. So one electron and one hole. They're always in pairs, electron-hole pairs. In other words, Ni should be equal to Npi. Okay? Once we apply the constraint, then we can calculate Ni equals Pi equals square root of the previous number, previous equation. The square root MCNV e raised to minus Eg over 2kd. So now you have a way to calculate the intrinsic concentration of carriers in any material as a function of temperature. Okay, it's a powerful equation. Now we can calculate how many electrons or holes there are. Okay, and of course, N naught P naught is N squared. So if you plug in the numbers, we need to, of course, know the crystal structure in order to calculate NC and NV, because these are the effective density of states at the top of the bottom of the conduction band and top of the valence band. And once we calculate that, those are constants. Of course, temperature dependent, but everything else is a constant, so you can look it up in a table or whatever. You can calculate that. So, for instance, in silicon, as we saw before, the intrinsic concentration is about 10 raised to 10 per centimeter cube. That's a very small number, by the way, to think about it. Remember, there are about 10 raised to 20 or so, 10 raised to 18 or so silicon atoms per centimeter cube. So the number of electrons, this is a very small number for intrinsic silicon, which means that silicon in general is an insulator. It's a poor conductor if you don't dope it. Okay. If Nc equals Nv, which, as I said before, is not true, but if it is, it's not true because the effective mass of the hole and the effective mass of the electron are not the same typically. But if it is, some material, let's say it is, then you can prove that the Fermi level lies exactly in the middle of the band. If Nc equals Nv, you can, from this equation, you can show that Ec minus Ei should be equal to Eg over 2. Remember, Ei is just the intrinsic Fermi level. Okay? Not terribly important, just to show that that's the case. In practice, Nc and Nv are slightly different. The hole and electron effective masses are different, as I said. So the Fermi level is slightly shifted from the middle of the band, even in the intrinsic material. Okay? So again, keep that picture in mind. Now, a convenient way to remember the carrier concentration. So this, I want again to emphasize what we have done today is we have calculated the concentration of the carriers in an intrinsic material, extrinsic material, whatever material, as a function of temperature, just purely from the crystal structure and temperature. Okay? It's a very fundamental number equation. So you should try to remember this. Of course, you can look it up because the quiz will be open up. But conceptually, if you want to learn, you should remember this idea. Okay? That N naught, the electron concentration, depends on Ni, the intrinsic concentration, multiplied by EF minus EI over KT. So now we have written in a slightly different way, where EF is the Fermi level of any material, minus EI, which is the Fermi level of the intrinsic material. Okay? Ni is, of course, the intrinsic carrier concentrations. You can write the same thing for the holes as well. P naught is, Ni is the same, so it's the same Ni, e raised to EI minus EF over KT. If EI equals EF, which means that the material is intrinsic, then of course these two sides are equal, and not equals Ni. Okay? In other words, the way to think about this is also Remember, EI lies in the middle of the band, or close to the middle of the band. If the Fermi level moves from the middle of the band up, the material becomes N-type. There are more electrons. If the Fermi level moves down below the middle of the band, the material becomes P-type. There are more holes. That's a way to remember this, by the way. Okay? I want you to keep that picture in mind. That's very important, actually. Okay? Now, okay. Let's see. Do we have time? Can't see the clock, actually. Okay, we have 10 minutes. Okay. Let me see what else I need to cover. Oh, we have a lot to cover. So I won't go through this example problem today. Well, I don't want to speed through this because it's a very important concept. I know a lot of this might seem very abstract and go over your head, and I had to go through these fast. And even though I went through it slowly. So I want you guys to go back and really think about this and look at the slides, okay? Think about it. But let's look at the example. I think it's worth going through it. A very simple example, okay? And I just pulled it from the text. A silicon sample is doped to 10⁻17 arsenic atoms per centimeter cube. Okay? Very straightforward. Remember, arsenic is a donor or acceptor. 5 electrons. Yeah, it's a donor. Remember, silicon has 4 electrons, right? Anything more will be donated. So arsenic has 5, it's a donor. Boron has 3, it's an acceptor. There's 1 less. Keep that in mind. Again, remember that picture also. It's very important. What is the equilibrium hole concentration at 300 Kelvin? What is the Fermi level relative to the EI, intrinsic Fermi level? Okay. So we are just applying the equations we just learned. Since the concentration of the donor is much larger than Ni. Remember, the 10⁻17. Remember, Ni in silicon is about 10⁻10. We know that. So I just saw that. 10⁻17 is 7 orders of magnitude higher, so it's reasonable. This approximation is reasonable. We can approximate that the number of electrons should be equal to the number of donors. Okay, that's a simple. Each arsenic atom will give you 1 electron, so the electron concentration should be approximately equal to arsenic concentration. That's the first simple thing we can do. Okay, so N0 is just Nd, 10⁻17 per centimeter cube. Okay. Now, of course, P0 and N0 is Ni squared, so very easy to calculate the minority carriers. P0 is the concentration of holes, the minority carriers in this N-type material. So Ni squared, Ni we know. At 300 Kelvin, we can look it up in a table or do the calculation from before. Okay, this is just the intrinsic carrier concentration of silicon. It's just that. 2.25 square would become 2.25 10⁻20 divided by 10⁻17, and you get that equation. Now, look at these numbers carefully. The whole concentration is 10⁻³ per centimeter cube. Electron concentration is 10⁻17 per centimeter cube. So clearly, there's a lot more electrons than holes. 14 orders of magnitude. Okay. Even then, to calculate current, we need to take these holes into account, which is why it's important to calculate. We'll see this next class, maybe next week, at this rate. Okay, so now, of course, to calculate where the Fermi level is. We know this is N-type. The Fermi level is to go closer to the conduction band. We know that. Okay, that's simple. So from the equation before, EF minus EI is KT ln and not ever. And I just plug in the numbers, so put everything in, you get 0.4 EB. Okay, so that's how you do the calculation. You have the valence band, conduction band, middle of the band is roughly the intrinsic Fermi level. The Fermi level in the presence of donor atoms is moved up closer to the valence band. Conduction band. Okay, so you should be able to do things like this. So make sure you go back and review. All right, the last 5 minutes, let's talk briefly about the temperature dependence of carrier concentration. We'll come back to this probably on Thursday. Okay. So far, we have only looked at quantitatively and qualitatively how many charge carriers there are. But how do the charge carrier distributions change with temperature? Turns out to be very important and very counterintuitive. So it's important to think about this also. Okay, the equations are the same. I just rewrote those. Okay. Temperature dependence, of course, comes there. That's obvious. That's not the only place. The temperature dependence also comes in the intrinsic concentration. Remember? The intrinsic concentration also increases with temperature. They're both increasing. They're not opposing each other, but they're both there. This is why it gets complicated. The two kinds of effects that goes on. Okay. Now, if we are able to explicitly write the intrinsic carrier concentration, which we derived earlier, it's square root NC and V e raised to minus EG over 2 KT. Okay. We derived this a couple of slides before. So we know the temperature dependence is there. Now, even inside this, we have further temperature dependence, right? Because these density of states are also temperature dependent, as we saw before. That's shown here. Okay. Both NC and NV. So, if you put everything together, you get an expression like that for the intrinsic carrier concentration as a function of temperature. You have an expression, which is T raised to 3 over 2, and then you have an exponential expression. Of course, which will dominate? The exponential. Okay? But you have two exponentials in this equation. So, of course, that dominates, and we can see what that looks like. Oops, sorry. So, another way to look at this is that if you are given the intrinsic concentration and the Fermi level relative to the intrinsic Fermi level, then you can calculate the carrier concentrations. Okay? Or, in other words, there are three unknowns here if you think about these equations. Okay? Because you will see this in your example problems and problem sets and so on. The three unknowns to some extent. Temperature, okay? The intrinsic concentration, and the Fermi level. If two of these are known, you can calculate the other. I mean, sorry, the four actually. The fourth one, of course, the carrier concentration. So if three of these are known, temperature is usually known. That's why let's say it's only three. Two of these are known, then you can calculate one of the other. Either where the Fermi level is, or how many carriers are there. Okay, so that would be the type of problems that you will be looking at. So keep that in mind also. Of course, if you have extrinsic and heavily doped, like we did in that example, we can make the assumption that the electron concentration is nothing but equal to the donor concentration. Okay, I think we'll stop here. There's a lot we covered today. So try to attend the